All right, hi everybody. My name is Colin Hill from Columbia University and the Flatiron Institute. I'm going to be telling you today about some work related to this broad theme of exploring cosmological concordance with data from the Automatic Cosmology Telescope, Planck, and future CMB datasets. And this is work that's been done with a broad set of people shown here who I'll highlight throughout the talk. Okay, so I just want to start with the first maybe thought about the situation as far as the data is concerned. This is a compilation plot that I've been periodically updating in the past few months, showing a variety of indirect cosmological inferences of H0, as well as more direct local universe model independent inferences of H0. I've tried to choose a variety of different approaches from the two different classes. You can find a longer discussion of some of this on Twitter. I don't want to go through all of these in detail, but I'll just say that from my perspective, it seems plausible that maybe 68.5 or something in that ballpark might be just about amenable to everybody still. So yeah, I think it's definitely still obviously a super exciting question, but I do think we should keep in mind the fact that we should be data-driven in all respects. Okay, so I'm going to first talk about our most recent cosmological results from the Automatic Cosmology Telescope. I'll go through that pretty quickly, discuss the concordance of our results with other cosmological probes, primarily from the CMB. And then I'll talk about some very recent work that'll appear shortly related to the analysis of upcoming CMB data, in particular ways to avoid biases that could otherwise arise on H0. And then I'll talk about some work that was completed in the past year or so related to the early dark energy model as an attempt to resolve the H0 tension. And at the end, I'll briefly conclude with a look ahead to the imminent future. Okay, so first let's start with ACT. So I'm just going to go through two of our papers from the past year, which are those most directly connected to cosmology, in particular cosmology from the primary CMB power spectrum. But there's a wide variety of results that we have that you should check out. So ACT is a CMB experiment in the Atacama Desert in Chile, where we have this beautiful CMB sky that we can look at. That's actually the ground screen around the telescope. That's a picture inside where you can see the actual telescope. We've covered about half the sky with ACT. Our wide area scans just started in the last few years. We've been observing overall with this telescope for the better part of 15 years with gaps off and on to upgrade the detectors and so on. And at this point, we've now taken data at actually at 5 frequencies, which enables significant control of foregrounds, although the results that I'll show here are based on the analysis of data comprising just 2 of our frequency channels. And this is a picture of our collaboration at the last in-person meeting that we had a couple of years ago. Okay, so as I mentioned, I'm just going to talk about 2 of our papers that came out in the last year or so. Iola et al., which focuses on the maps, data products, and cosmological parameters, and then Choi et al., which covers the power spectra, which underlie the parameter results and some consistency tests and other aspects of the data analysis. But there's a variety of other exciting papers, including component-separated maps of the CMB and Compton-White parameter, which I was deeply involved in. Large catalog of SU selected clusters, lensing maps, ACT plus Planck combined maps, and a whole bunch of other things. So check it out. This is pretty much all on Lambda, the NASA server. Okay, so I'm specifically going to focus here on our cosmology analysis from ACT DR4, which comprised the analysis of data collected only from 2013 to 2016. So that we've collected a huge amount of data since then. So everything that I'm showing you here is first taste. Everything is going to be much more statistically precise when we analyze the data that we currently have on hand. So ACT DR4 comprised this wedding cake survey strategy. So we have a few regions that are much deeper than others. The ones labeled deep 5.6, deep 5, deep 6, deep 1. Those are the deepest regions with lower instrumental noise. And then we have these wider scans that covered a big chunk of sky. The total sky coverage is about 17,000 square degrees, but the cosmology analysis using the power spectrum from this data release is in the deepest 5,400 square degrees. So just to give you a taste of the data, here is a patch of sky covering about 600 square degrees. This is the sky at 150 gigahertz as seen by Planck. And then here's what you get when you add in the ACT data. So this is actually ACT plus Planck. Planck helps with resolving the largest scale modes that we lose to the atmosphere. But if I flip back and forth, you can see this beautiful improvement in fidelity as you add in the ACT data on small scales. And we can resolve things like radio and infrared point sources that you see as positive red spots in these maps, as well as the blue shadows, which are SZ selected clusters. All right, so fast forwarding through years and years of very hard work, these are the foreground marginalized CMB power spectra inferred from ACT DR4. So we have the temperature power spectrum, the E mode power spectrum, moderate detection of the B mode power spectrum on small scales from gravitational lensing, and then the TE power spectrum down here. And then this is folding in the data from all the other, well, many of the other CMB experiments at present, including Planck, SPT, Polar Bear, and Bicep Keck. And you can see we have this beautiful picture covering a vast range of angular scales, which is well fit, certainly by eye, by this simple model, which is pretty amazing. Okay, so let's get into some of the quantitative details. So one of the great things about ACT, first of all, is that it's a completely independent check of the satellite data from WMAP and Planck, which at this point, we're starting to have comparable statistical precision to those experiments. In fact, we are, I think, better than WMAP on a number of parameters. The first baseline point is that lambda CDM is a good fit to the ACT data. Quantitatively speaking, if one assesses the consistency of the ACT lambda CDM parameters with those from WMAP and Planck within the lambda CDM parameter space, we're consistent roughly at the 2.5 sigma level with those experiments. So no evidence of tension really. There's a minor difference in the NS omega baryon H squared plane, but that really traces back to the fact that we don't measure the first peak in the TT power spectrum with ACT due to this atmospheric noise that I mentioned a minute ago. So given this consistency, we can then combine ACT and WMAP to form a data set that has statistical power that gets close to Planck, where this data is not quite at the Planck statistical sensitivity, but the data that we have on hand post 2016 will certainly get us there. So let's do that. So the purple contours here are ACT plus WMAP. The light blue is Planck, and then one can also look at ACT plus Planck. But the most interesting comparison, I think, is the purple to the light blue, where you can see that indeed ACT plus WMAP, which is totally independent of Planck in terms of the instrumental systematics and so on, yields lambda CDM parameters that agree very nicely with Planck. So we can zoom in on H0, since that's the purpose of this conference. This is the marginalized 1D posterior on H0. Then you can see that, as I said, ACT and WMAP agree very nicely with Planck, albeit with slightly larger error bars. So quantitatively, ACT plus WMAP, we have H0 of 67.6 plus or minus 1.1. As you probably imagine, we do a wide range of consistency tests to make sure that there's no evidence of systematics or other issues. I'm not going to go through all these in detail, but suffice to say that across all these different ways of slicing and dicing the data, indeed our H0 results are quite stable. Okay, so putting these into context, here's a whisker plot that shows ACT plus WMAP in yellow, or ACT alone in this yellow point, versus the other CMB experiments, Planck, for example, WMAP, and so on, versus a few of the local universe measurements, so the TRGB calibrated supernovae from Friedman et al., and then the Cepheid calibrated supernovae from Rees et al. And I've amended this plot from the published version with the very latest 2021 Rees et al., which moved down a bit. So actually using that latest result from Shoes, the tension drops a bit. So it would have been 4 sigma with this previous point. Now it's about 3.3 sigma between ACT plus WMAP and this Shoes 2021 from Rees et al. And alternatively, if one looked at the Friedman point here from TRGB, there's roughly 1 sigma agreement, as you can see with the error bars explicitly. Okay, so that's kind of the current state, a very lightning overview of the current state. We are actively analyzing the very large amount of data that we have on hand from ACT, so stay tuned for updates. In the context of these more precise measurements, I've been thinking hard recently about things that we might need to keep in mind as we analyze that data in order to make sure that we robustly infer cosmological parameters. So I'm going to highlight some recent work that will appear on arXiv in the next week or so with Fiona McCarthy and Matthew Matavachero from the Perimeter Institute. And this concerns potential biases that could arise in the inference of H0 due to nonlinear CMB lensing effects in the CMB power spectrum. All right, so CMB lensing, this is a one-slide overview of the impact of CMB lensing on the CMB power spectrum. So this is the TT power spectrum in the top left, EE top right, TE in the bottom left. The TE is being shown on this funny SimLog scale that lets you plot positive and negative values on a logarithmic axis. And what I want you to take away is just that as you go out into the high L tail, the effect of lensing, which is in the lens power spectra are in blue and the unlensed are in orange, the effect of lensing is significant and in fact dominates as you get out beyond L of 4,000 or so. And the ratio between lensed and unlensed is shown down here in the bottom right. The noise curves here for the Simons Observatory in green and CMBS4 in red. These include the effect of foregrounds, component separation, as calculated by myself for these two experiments, and those are available online if you'd like them. Okay, so it's a large effect. Now, what has been recognized and known, I think, for a while is that the effect on the matter power spectrum of nonlinear gravitational evolution, baryonic effects, for example, from AGN feedback and supernova feedback, this propagates into changes in the lensing power spectrum. So that certainly was known. However, that then propagates into changes in the primary CB power spectrum at a level that hadn't been appreciated, I think, previously, which is what motivates our paper that will come out shortly. So here we're looking at the ratio of the predicted lensing power spectrum in the top left versus a dark matter only calculation. This is a nonlinear dark matter only calculation using the halo fitting function. But you can see this suppression in the lensing power spectrum due to these feedback prescriptions as implemented in this variety of cosmological hydrodynamics simulations that are listed down here. For example, the illustrious TNG simulations, Bahamas, Owls, and Horizon. Now, we can then turn those changes in the lensing power spectrum and compute how they change the predicted primary CMB power spectra, which is just what's shown in the other three plots here, TT, EE, and TE. And what you can see, let's say just looking at the TT plot, is that as you go out beyond L of, say, 3,000, 4,000, you're getting multiple percent level changes in the TT power spectrum. And our data is going to be so incredibly precise that even these subtle effects actually start to matter, which is kind of interesting. We usually don't think about AGN feedback having an impact in the primary CMB, but here it is. Okay, so I'll show you the consequences in just a second. What's currently done in primary CMB analyses and forecasts to date is basically what I call set it and forget it. One basically, adopts some halo fit or HM code fitting functions in CAM or class. These are the default modules, and then you just run your analysis and kind of forget about any issues. But that approach will not suffice for the analysis of Simons Observatory and CMBS4 data, as I'll show you right now. So here is the fractional bias in units of sigmas on the different cosmological parameters one might be interested in for CMBS4, where one analyzes the data assuming this standard approach, say halo fit, for modeling the nonlinear power spectrum, but the true power spectrum was actually generated with this hydrosim, in particular the Owls AGN simulation. And what you can see is that as your data gets precise enough and you're going out to Lmax values, or Lmax is the maximum multipole used in your analysis, you get to Lmax values of order a few thousand. These biases on some of the parameters crop up to being larger than a sigma. In particular, for CMBS4, if you analyzed the data in this way, you would get a 1.6 sigma bias on H0, 1.6 sigma bias on the cold dark matter density, and a 1.2 sigma bias on N effective. So these are significant compared to the statistical error bars. And this is just for one particular hydrosim. For the other ones we tested, they're similar, but there's no guarantee that any of these simulations are the actual truth. Although we think that they are, the best current things on the market. I do want to emphasize this is not an issue for current data from Planck, certainly, which has Lmax down near 2000, and it's also not an issue for current ACT and SPT data, but we're not far away from this starting to become an issue. Okay, so we have at least 3 ideas we thought of to fix this problem, and I think they all will work. The first one is to explicitly cut out all of the TT data at L beyond 3000. So you pay a small penalty in the statistical error bars because you're throwing away some of your data, but that is the region that's most affected. And the reason is just that the fractional effect of lensing is largest in TT because the gradient in temperature is larger, and on small scales, you're just seeing basically the lensing of this gradient. And then secondly, it's because the number of signal dominated modes that we measure in temperatures is larger than it is in polarization. So if you just check out all that high LTT data, you can basically remove this bias with a moderate penalty in the error bars. Another thing you could do is actually just introduce some new parameters that characterize these baryonic effects, and then marginalize over those. So that's what's shown in this plot. Again, looking at these different parameters, but now including explicitly these additional baryonic parameters in the model and then marginalize over them. And all you need to really take away is to just look at the scale on this plot and notice that it's much less than a sigma. So as soon as you do this, your fractional biases become statistically negligible. And then the last approach that we've thought about so far, and I think probably is what we'll end up wanting to do with the data, is to actually delens the temperature and E-mode maps using your reconstructed lensing convergence kappa map, or external tracers like the cosmic infrared background. This is nice because it's robust and data-driven. You know that the lensing potential you're using is the truth because it's the one that's in the sky. And in fact, it was shown a few years ago now that this approach can actually improve the error bars on parameters. So what previously had seemed like a good idea for the purpose of reducing covariances, as highlighted by this paper, actually turns out to also be important for removing biases. So I think this even more strongly motivates the need for delensing in T and E, in addition to delensing in the primordial B-mode search, which we already knew was important. Then the final comment I wanted to make here is just that in the course of doing this, we've also learned that we're going to have to be more careful about how accurately we compute things numerically in our Boltzmann codes. The default settings in CAM or class actually don't suffice for the analysis of upcoming data sets. The biases that one can get from using the default accuracy actually are even larger than these baryonic biases I just showed you. This is a similar type of plot showing the fractional bias in units of sigma for using the default accuracy versus a very high precision calculation. And you can see the biases are multiple sigma in this case. This is easy to fix, of course. You just have to turn up the numerical precision parameters in these codes, but we now know that this is important. And in fact, just an aside here is that even for current data from ACT and SPT, if you want to do a precise chi-squared comparison of the best fit models for lambda CM compared to extended models like early dark energy that I'll talk about in a second, actually you need to use the increased accuracy settings to get these best fit chi-squareds fully converged. Okay, so in the final part of the talk here, I want to discuss the early dark energy resolution or attempted resolution to the Hubble tension and place this in the broader context of cosmological concordance. This is work that was done in the last year or so with my collaborators, Evan McDonough, Michael Toomey, Stefan Alexander, Misha Ivanov, Marko Simonovic, and Matthias Zaldarjaga. All right, so the motivation of this EDE model, as I mentioned, is to resolve the Hubble tension. I think many people have heard about this, so I'm going to go through this part relatively quickly. But the basic upshot is that if you look at lambda CDM fit to a variety of cosmological data, there's this tension between H naught and the direct shoes measurement. And in the early dark energy model, this could be at least mostly reconciled. If one focuses mostly on a fit to just say Planck plus local H naught data, for example, from shoes. So physically, this works by decreasing the size of the sound horizon imprinted in the CMB. I suspect most have heard the basics of this story before. The sound horizon is the integral of the sound speed, CS dz over h of z, from the beginning of the universe to the time of recombination. So in lambda CDM, the only parameters that enter that quantity are the baryon density, the cold dark matter density, and the photon density. In early dark energy, as we'll see, there's additional parameters that impact it. The reason that this is important is that we actually measure the angular size of the sound horizon, theta S star, which is basically the inverse of the peak spacing in the CB power spectrum. Now, if you want to hold theta S star fixed, if we then decrease RS star, then we'll be decreasing dA star, the angular diameter distance, and thereby will be increasing H naught. So it, the basic shifts go as one would like them to. All right, in EDE, we'll introduce some additional parameters that are going to affect this, this quantity. I'm going to skip past the microphysics of the EDE scenario in the interest of time, just take you to the phenomenological parameterization that's being used to analyze the model. So in this picture, we have some fractional contribution of this new field, this EDE field of the cosmic energy budget, which is tuned such that it becomes important just prior to recombination, prior to which it's acting as dark energy, hence the name, and then it rapidly decays away so as not to disturb the rest of cosmology. So the parameters we use are FEDE, which is the maximum fractional contribution of this field to the total cosmic energy budget, which occurs at some redshift, ZC. And in the microphysics, this is related to the redshift when the field starts to roll down its potential. And then the final parameter needed is just this initial condition, theta I, which says where did this field start on its potential. So there's 3 additional parameters here in this model compared to lambda CDM. One thing to keep in mind is that there's a highly nonlinear relation between these effective parameters and the actual physical parameters that appear in the potential, like the mass and the decay constant of the field. And if one does the analysis in terms of those parameters, the conclusions actually can change a bit. All right, so why should we care about this? Well, it turns out that if you analyze the Planck CMB data in the context of this model, you can maintain a good fit to Planck while yielding a relatively higher value of H naught, as pointed out by Poulin, Smith, Agrawal, Lin, and others in the past couple of years. And physically, again, this is just due to the decrease in the sound horizon. Although I want to emphasize that one important aspect here is to include the perturbations in this early dark energy fluid, this early dark energy component, rather, and not to neglect those. So it's important to compute the fluctuations self-consistently to get the details of this calculation right. Okay, so where we came in was to first look at the matter power spectrum in the context of this model. So here I'm showing a calculation of P of K in lambda CDM in black compared to the EDE model in dash red, where these are the same models that I just showed you in this previous slides. They both fit the CMB quite well. And you can see that if you look at the ratio of these models, there's pretty significant differences on the order of tens of percent over wave number ranges that we do have data in, which suggests that there's going to be constraining power on the model from large-scale structured data. All right, what's the origin of this difference in P of K? It actually traces back to the parameter shifts in the early dark energy scenario. So looking at this paper from Smith, actually one could kind of pick up what was going to happen. So the first big shift that we notice is in the cold dark matter density omega CDM. And the reason that this has to increase in EDE as compared to lambda CDM is that the early dark energy field is acting to slightly suppress the growth of perturbations prior to recombination when it's dynamically active, similar to the way that dark energy today is suppressing the growth of perturbations. So to compensate for this, the cold dark matter density has to be increased. This is an early ISW effect that we're compensating. There's a scale dependence to these effects. And in order to compensate for that, there's a shift in NS, which is also required. So NS actually has to increase. You need a bit more power on small scales. And the upshot of these changes is that sigma 8, the late time amplitude of fluctuations, and omega m, the matter density, change a bit as well. And this is captured in this S8 parameter that is conventionally used in weak lensing studies. So S8 goes upward. All right, so we came into this, and one of the first questions that I was interested in asking, which hadn't been looked into before, was to just see what the CMB alone had to say about this model. So let's just fit Planck 2018 primary CMB data, not lensing, primary CMB, and see what we get. So that was what we did. These are the full posteriors. Lambda CDM is in red, EDE is in blue, and the shoes 2019 constrained from Riesetal is in gray here. So what you basically see skimming over these is that there's no big shifts that are seen if you fit just the CMB. And in particular in the H0 panel here, the H0 tension persists. Planck doesn't on its own want to move up into this higher H0 region. And that's seen in the posteriors on these extended EDE parameters, which I'm showing you here. So FEDE, this parameter that quantifies how much of this early dark energy is around, is peaked at 0, and one just gets an upper bound. All right, so now let's skip ahead to a global analysis where we fit this model through everything, including the DES data, hybris prime cam data, the kids weak lensing data, and not including any local H0 data. So we're just gonna say in the context of the cosmological measurements, what do they yield if you fit this EDE model? So that's what's shown here. Again, lambda CDM in red, EDE in blue. And again, skimming over these panels, you see, there's some small sort of shifts in omega CH squared, for example, but there's not any major shifts. In particular, H0 does not move up to be consistent with the local shoes measurements, for example. So there's a broadening of error bars because there's more parameters in the model, but there's no major shifts. And if we zoom in on the H0 panel, I think it's relatively clear. So we can look at this then in the context of the EDE parameters. Here, red is now showing you the fit to all data sets, including shoes in the analysis, and blue is the fit to all data sets without shoes. So the blue is what was shown here as well. So if you don't include shoes, then you just get this upper bound of FEDE less than 0.06. And if you look at H0, you see this blue curve here compared to the gray, there's almost 3.5 sigma tension between the indirect cosmological model inference of H0 and the direct H0, even in this broadened EDE parameter space. So I would say at that level, it's risky to even combine the direct shoes measurement, but if you do, you get the red posteriors that I'm showing here. Okay, so that was where things stood, I guess, in the spring of last year. We then wanted to actually put even more precise constraints in this model. So to do this, we folded our modified class code, class EDE, into the effective field theory of large-scale structure likelihood that Misha Ivanov and others had developed for the BOSS galaxy power spectrum data. So skipping over all that work and just showing you the results, this is what we found when we did that. So green here is showing the fit to Planck alone, which I showed you a minute ago. Blue is Planck plus this BOSS EFT likelihood plus the S8 data from DES, HSC, and kids. And then red is lambda CDM fit to those the last three things I just said a minute ago. So the takeaways here are that when you include the BOSS EFT data, you actually tighten up the constraint on FED even further. You get this upper bound of about 5% of the universe ever having been in this EDE field. And the tension with shoes increases accordingly to about 3.6 sigma on H0. If you look at this, you can just see that H0 is not changing compared to its lambda CDM value that's given in red here. What's responsible for this increased precision in the constraints? It's really coming from the constraining power on omega CDM in this EFT BOSS likelihood. So the shape of the matter power spectrum is being probed in this first principles calculation of the galaxy power spectrum. And what's cool is that this is a case where you actually do see gains coming from using the EFT-based likelihood instead of the standard galaxy power spectrum likelihood based on redshift-based distortions and BAO. And if you compare the blue curves here basically to the red curves, you can see that indeed there's tighter constraints coming from the red curves. So I think this is a nice illustration of the power of this, this theoretical approach. The final quantitative thing I want to address here is there have been some suggestions that prior volume effects might be responsible for these tight constraints that are being seen. We addressed this in detail in appendices, in particular in this paper from June, where we compare frequentist and Bayesian approaches for the inference. So what I'm showing you here are the usual marginalized constraints that we see in a Bayesian approach are in the solid thick curves here, where red is for the BOSS full shape EFT plus Planck, and then the blue is also including the S8 data. And then the thin curves are showing you the best fit log likelihood profile, where what we do is at each value of FEDE, we find the best fit point in parameter space looking through all of the other parameters in the model. So first, let me point out that the overall global best fit point is down here at FED around 0.03, which is quite far from the FED that's needed to resolve the Hubble tension of about 10%. And the gain in chi squared over lambda CDM is about -4. So we have 3 additional parameters in this model, as I told you earlier. So this is pretty much what you would expect if you introduce 3 new parameters. Your chi-square changes by a few. If one then looks out in the tails toward this region where you have the H0 resolving models, first of all, if the S8 data is included, then these two curves basically agree anyways, and there is clearly not a strong preference for such large values of FEDE. If one ignores the S8 data, which I don't think is a fair thing to do, then you look at these red curves, and there is some difference that's seen here, which tells you that if you tune all the other parameters in the model, you could find some FEDE value around 10%, which has a chi-squared that's a bit worse, but maybe comparable to lambda CDM. However, one might ask, how tuned are those parameters? The way to look at that is to then look at the mean likelihood profile. So that's what's done here. So what we do here is, for each value of FEDE, we take the samples from the MCMC chains and then compute the averaged log likelihood profile, averaging over all the other parameters. So this basically says, on average, how much is the chi-squared improved by this additional component. This tells you whether fine-tuning of the additional parameters is important or not. And what we see is that these two curves look remarkably similar. This is for the full shape BOSS data plus Planck only. So not even including the S8 data, which would push these, of course, to be even more strongly peaked at FED equals 0. Yeah, so the takeaway here is that these two curves agree quite nicely. The marginalized constraints in the Bayesian approach are solid, and the dashed curve here is this frequentist mean likelihood based approach. The fact that these two curves agree tells you that prior volume effects are small and certainly not contributing more than a sigma of the final constraining power. So I think we have a pretty robust picture of what's going on here. I think I've probably gone over my time, so let me just wrap up by saying that after we finished this work in the summer, there was this nice paper that came out in the fall from Jademzik, Pagosian, and Zhao, where they basically generalized some of these constraints on sound horizon reducing scenarios like EDE, but generalized it to the whole class of such models, and showed how you basically inevitably run into conflict with either BAO or weak lensing constraints. I won't go through this in detail. Instead, I'll just advertise their paper here. And I found this to be quite an interesting and nice generalization. And I'll also point you to a very recent work from just a week or two ago by Lin et al., which looked at a different, I'd say, different way of doing things, but drew similar conclusions. All right. In my last slide or two, let me just look ahead to the future very briefly. So as I mentioned, we've been continuing to observe with ACT. We're going to observe through the end of 2021 with ACT. SPT is also taking great data with SPT3G. If you forecast our constraints on H0 with the full ACT data set, we expect to get to a sigma of H0 about 0.5 kilometer per second per megaparsec in lambda CDM. Even more exciting, though, I think, is that we can actually look for small deviations beyond lambda CDM. So here's just one example, looking at EDE versus lambda CDM. The bottom plots are the fractional differences between these models for the 3 main power spectrum channels that we have. And you can see that there's differences. They're small, but they're non-zero, such that with high precision data over a wide range of multipoles in these 3 different channels, one can really hope to look for such subtle deviations from lambda CDM. And then finally, looking a little bit further ahead to Simon's Observatory, the H0 constraint will improve yet further by about another factor of 2 in lambda CDM. SO is going to start taking data in just a couple of years and will improve the noise level another factor 3 below that of ACT with 6 frequency bands, roughly arc minute resolution. So it's going to be pretty fantastic. And then a bit further along, around 2027, 2028, CMBS4 is slated to start as well, ramping this up even further, another factor of 3 or so, factor of 3 or 4 below below SO in terms of the noise level. So the future is really, really bright. Okay, so I'll just wrap up with my take homes. We have concordance from the CMB. ACT DR4 matches Planck quite nicely. I think systematics in the CMB are ruled out as a source of the H0 tension. There are interesting effects related to nonlinear CMB lensing that will need to be taken into account in upcoming CMB analyses, as I mentioned, but we know how to deal with them. I think it's an interesting case where there's subtle effects that we hadn't thought about before, but we already have the solutions to handle them. This early dark energy model, as I mentioned, appears to not be able to simultaneously be concordant with all the data sets we have in cosmology, for which I think means that theorists simply need to go back to the drawing board a little bit. I don't think that all hope is lost by any means. And then lastly, as I mentioned, the future is very bright. While the wide variety of early universe resolutions to the H-naught tension predict clear signals in the CMB, and it will be very exciting to look at them with instruments, for example, like SO and CMB S4. So thanks a lot, and I apologize that I went a bit over time.